of whether hot is the way to do mathematics. But I am going to make the question more precise, and this is a definition due to David Roberts from a couple of days ago on the hot chat. And it's the kind of mathematician that I am. So a generic mathematician, or more precisely a generic pure mathematician, is a mathematician that's working in the kind of the areas traditionally represented in mathematics departments around the world. So algebra analysis, geometry, topology, and number theory. These kind of mainstream areas, if you like. These are areas traditionally represented in most mathematics departments. And these people working in these areas are traditionally using, not all of them, but many of them, are using classical logic and the axiom of choice. And so a person doing all of those things, let's call them a generic mathematician. And I'm going to use that phrase throughout the talk. And I've been looking for months now for a phrase which somehow doesn't offend people. It's difficult to find. So I'm going with generic mathematician in this talk, and it just means the kind of mathematician that I used to be, or the kind of mathematician that I am, if you like. So in most mathematics departments, most of the pure mathematicians who work there are generic mathematicians. Of course, there are people doing logic, there are people doing type theory, there are people doing foundational work, but these are not covered by my generic mathematician definition. So I've been a generic mathematician for 25 years. I'm an algebraic number theorist working at Imperial College London. And a few years ago, I got interested in formalizing mathematics on a computer. And initially that was because I was interested in using it for teaching, but now I'm interested in using it for everything, teaching and research. And the big question is, you formalize it on a computer, you have to choose a system. And I think a very important question is, which system does one choose? So in some sense, this talk is some kind of summary of where I am with my struggles trying to answer this question. So here's what will happen in the talk. Firstly, there'll be a couple of slides of propaganda, why I think mathematics should be formalized, and also especially why I think generic mathematics should be formalized. And then secondly, we're going to talk about one very precise question, which comes up very early on when you're deciding which system to use, which is the univalence axiom. And then thirdly, I'm going to talk about practical experiences I've had formalizing MSc level algebraic geometry in a theorem prover, in the lean theorem prover. So, okay, oh, that's interesting. I can't quite see what I've written because of some mild pop-up. Okay, why formalize mathematics on a computer? So here are some traditional reasons for formalizing mathematics on a computer. I've talked to a lot of mathematicians and a lot of computer scientists about why mathematics should be formalized. And the obvious reason, as far as the computer scientist is concerned, is you formalize it, then it will be correct, right? This is why these systems exist. They have been developed, many of them were developed to verify that computer programs have no bugs. And it's in some sense a coincidence that the same systems can also be used to check that theorems have no errors. So computer scientists say, well, it's great to formalize. The mathematical literature is riddled with errors, and so you should formalize it because then things will definitely be right. And this is absolutely rejected by mathematicians because already we know that our theorems are right. That was somehow, we've been doing it for thousands of years on pencil and paper, and we've got a great theory and it works fine. Of course it's right. We don't need this kind of extra checking that computers, an error in a theorem can often be worked out. It's quite different to a bug in a program. A bug in a program can cause trouble, right? Most errors discovered in theorems are just fixable and somehow are fixed. And we don't fix the papers, but somehow they're somehow unimportant minor errors in theorems. Mathematics is basically fine. So another complaint is sometimes arguments are left to the experts. And when the experts die out, there'll be holes in our literature. And again, this is completely not interested in that objection, because what happens is old papers tend to be replaced by newer papers. Newer papers come up with better ideas that do more stuff in a more efficient way using more sophisticated techniques. And in general, mathematics seems to survive the fact that experts die out because it just grows more quickly. And somehow the final thing, there's this list of 100 theorems, which, 100 challenges for mathematicians, computer scientists, 100 challenges. Why don't we formalize these 100 theorems? And one of the theorems on the list is Fermat's last theorem. Why don't we formalize the hundreds, thousands of pages of all the mathematics that goes into the wild setup proof of Fermat's last theorem? Wouldn't it be sort of just intrinsically an interesting thing to do and verify that all the complicated algebraic geometry used is all fine? And the answer is no. I've asked many, many number theorists, would you be interested in seeing a fully formalized proof of Fermat's last theorem? And the answer is simply, we don't buy it. We don't see the point. The proof is fine. The proof has been generalized out of all, out of all comprehension in the 20 years, 25 years since it's been proved. It's been completely understood. There is no point in formalizing it. We've got the paper proof. An expert can read the paper proof. It's absolutely fine. So these, it turns out, are reasons to formalize mathematics which don't seem to interest generic mathematicians, rightly or wrongly. So we have to come up with other mathematicians. We have to come up with other reasons, perhaps, because it's the generic mathematicians we want, right? The generic mathematicians, this is an uncomfortable truth, but the generic mathematicians are the ones who are deciding who gets the Fields medals. They're deciding who gets funding, on the whole, they're deciding who gets promotions. And they also have a large say in deciding what's fashionable. They know which areas are moving quickly. And the generic mathematicians are somehow, many of the most important mathematicians in the hierarchy are generic mathematicians. So it's kind of important to have them on board. So here are some others, here are some other goals which might convince generic mathematicians. So I think this is the last page of the propaganda. Here are some other goals which might begin to make generic mathematicians begin to understand why this is a good idea. Maybe we're going to be able to start creating tools where instead of having to grind out several pages of tedious calculations on paper, you kind of know they're going to work, but you need to check that they work. And you kind of feel that you should give a nod to these arguments in your paper, even if you're not going to write them in full. It would be good. Why not just throw it over to the computer and say, can you just verify that following your nose will prove these theorems? So we'll get a digital graduate student that will be prepared to do, be prepared to do jobs like this, jobs that I run into, just in my normal daily life as a generic mathematician. Another thing is search. Google is, and other search engines, they are not great for, if I want to know, does every ring with property X also have property Y? If you're lucky, someone's asked precisely that question on Math Overflow, and Google will spot it.
Excuse me, Kevin. We've got a question from Tim Richter.
Hello.
Go ahead.
Ask a question. I didn't raise my hand or whatever. I'm sorry.
Oh, no problem at all. So your hand is raised, but don't worry about that. If we only have
I'm sorry.
We have one teething problem today. We've done very well indeed. Okay, back.
I like the way that you scribbled on my slides there with a kind of a green pen. So, secondly, it would be nice to create a searchable database of known mathematics, because I have very precise questions which I want to know the answer to, and Google won't tell me the answer. The best way to find an answer to a precise question is to start knocking on doors. Just ask the person in the office next to me, ask the next number theorist along, and then ask the one after if they don't know. And if I ask 5 and none of them know, then ask some other mathematicians, start emailing people. If we could somehow automate that, that would be a very interesting and useful tool. And this is one of the things behind Tom Hales' Formal Abstracts project. I should have really mentioned Tom Hales. Tom Hales' I'll mention him verbally. Tom Hales' Formal Abstract project. This is one of the major goals in his project. And why not create training data for an AI, right? Machine learning works best if you have a lot of training data. And at the minute, these people are quite scuppered because they want to train their theorem provers, they want to train their algorithms on formalized mathematics, but the amount of formalized mathematics, especially sort of formalized generic mathematics, there's not that much around. There's not that many large databases which are somehow useful for these people. So there's 3 things which are sort of easily accessible and might change things. But there's just a general principle that digitizing things is a good idea. I mean, we digitized music, and now we have Spotify. You know, we digitized books, and now we have illegal PDF downloads of every book. You know, digitizing things changes things. I mean, maybe having illegal books or everywhere is not such a good idea. Who knows? I mean, digitizing things is progress, right? And we don't really even know how much mathematics is feasible to digitize, but the evidence is appearing that actually maybe a substantial amount of it, it might be, you know, you might be able to get one system that can understand a substantial amount of it. But, you know, there's a lot of things that aren't known because a lot of generic mathematicians aren't involved. And I just think that, you know, it will have unintended applications. So I think we should digitize mathematics. So that's the end of the propaganda. So now I want to talk, you know, now I want to actually talk about things of, you know, more of interest to experts. So let's now talk details. So it would be good to have a lot of generic mathematics in one system. And so now the question is, what properties do we require of the system? And the answer is, I think that if we want to get generic mathematicians involved in formalizing generic mathematics, we have to come up with a system which is the kind of system they're used to. So in particular, we have to allow classical logic. The law of the excluded middle is something that they use all the time. And many constructivists have said to me, actually, classical mathematicians are just naive. They use it when they don't need it. And maybe that's true, but they use it, and it's going to be difficult to persuade them not to use it. They use the axiom of choice, again, a non-constructive axiom. And again, sometimes they use it when they don't need it, but actually sometimes they use it when they do need it. You know, logicians have proved the various standard things that are used all over the place in mathematics are equivalent to the axiom of choice. They use dependent types, even though they don't know they're using dependent types. They use functions where the type of the value of the target depends on the input. And they use serious automation because we know what the axioms of a ring are, but we don't constantly use the axiom. We operate high above the axioms. A lot of, you know, we operate high above the axioms. We don't want to deduce everything from the axioms. We just want to type some generic, solve this problem for me, and the system follows its nose and solves the problem. So that's where generic mathematicians work, and it's going to be difficult to convince them to do anything else, I think. So we need to find a system that can do all of these things. And already this rules out a lot of interactive theorem provers that currently exist. So serious automation seems to rule out the set theory systems. And I think this might kind of just be a coincidence that the set theory systems happen to coincide with the systems with very little configurable automation. I don't really understand why that's happened, but on the other hand, you know, set theory is kind of like doing mathematics in set theory is kind of, it sort of feels to me like, you know, writing code in machine code, writing computer code in machine code, whereas doing mathematics in type theory feels more to me like writing mathematics, you know, writing code in Python. So you can just imagine that, you know, Python is just a more expressive system. So that might have something to do with it, I don't know. But even though mathematicians all use set theory, my empirical observation is that it's not that difficult to persuade them that type theory is just the same as set theory, really. And so the dependent types is the other issue, which seems to rule out a lot of these, well, essentially all of these higher order logic systems, which is a great shame because Isabelle Hall in particular has a huge amount of generic mathematics in it. You know, typically a lot of kind of classical 19th century analysis, for example, early 20th century results in analytic number theory. But is it really good enough for the kind of modern structural mathematics which we do? These systems, I think that it might be a fight to get these systems to do modern algebraic geometry. So I want to, at least for this talk, kind of rule out these systems that don't have dependent types, even though they're clearly useful for doing a lot of mathematics. They just don't quite fit in my, my possibly naive view of getting, serious modern generic mathematics in. So here are examples of systems which survive. Lean and Cock, both dependent type theory, and also various ways of doing univalence. So libraries that sit on top of Cock, but that kind of there are certain rules. You can't use all of Cock.
Excuse me, Kevin. We've got a question from Peter Lumsdane. Go, Peter.
Hello. I just had a quick question about your previous slide. Of all the features you're saying that the system needs to have.
Go, yeah.
There's sort of the two different ways a system can have those features. It can have them baked into the core, or it can have them as an interface on top of it.
Yeah.
And are you sort of being open-minded at this stage about which it could have, or are you saying it wants them at one or the other level?
Oh, well, I mean, you know a lot more about these things than me. I want to talk about univalence. And so I want to at least convince you that univalence is somehow a key dichotomy in what we have. Maybe if you can bolt on all of these things onto Mizar, that would be great. No, I'm quite happy to accept doing mathematics in any of these systems, as long as you can give me those 4 bullet points above. Yeah, I don't mind whereabouts in the system it is. I just want to make sure that a generic mathematician has easy access to it. Is that an answer?
Yes, thank you, Tabitha. Yes, thank you.
Shall we carry on? Thanks, Peter.
So Lean and Cock use dependent type theory, and they, as far as I can see, are fine for doing generic mathematics. And there are 2 interesting Cock libraries that have an extra axiom, an extra axiom called the univalence axiom, which is not present in Lean and vanilla Cock. And if we're still at the level of discussing what are the axioms, then I think that this is somehow, a question which needs to be resolved. Do we want univalence in our system or not? So what is univalence? I'm going to give you a formal definition on the next slide. I'm well aware that many of the people watching will know exactly what it is. Univalence is an axiom that somehow came out of the work of Voevodsky and Awady and Warren, just people thinking about homotopy type theory. And it's an axiom that sort of changes things fundamentally. And so a question that I really don't know the answer to is, does a generic mathematician want univalence or not? So this is really somehow what the rest of the talk is about. Do we need univalence? And I've met many people with very strong opinions on this. And in particular, I've met people with strong different opinions about the answer to this question. So I think it's this is not a precisely formalized question, but I think it's a question that's definitely worth thinking about. So let me tell you about the univalence axiom, and let me first say that the system that I've done by, the only system I know, really, the only system I know well is Lean, and Lean does not have the univalence axiom. And the reason it doesn't have the univalence axiom is because in Lean's type theory, propositions are proof irrelevant. So every true false statement, if it's false, it's got no proofs, and if it's true, it's got 1 proof. Right? Any two proofs of an equality, any 2 proofs, for example, of an equality, or just any mathematical theorem in Lean, any 2 proofs are going to be equal by definition. And this isn't quite, mathematicians are somehow not quite comfortable.
Excuse me, please, Kevin. We've got a question from Nick Hu.
Hi, Kevin. Sorry, I perhaps should have asked this a bit earlier, but when you were talking about the different proof assistants, I noticed that you didn't mention Agda.
Yeah.
Any of these, but
Agda can totally, Agda can absolutely go in. I would happily, Agda can go there, no problem at all. The only reason I didn't mention it is because my impression is that on the whole, Agda users are not particularly interested in formalizing generic mathematics. My impression is they're much more interested in type theory and applications to programming.
Right.
But Agda, absolutely, Agda's in.
All right, thanks. Back to you, Kevin.
So Lean doesn't have univalence. And sometimes mathematicians do discuss informally about whether two proofs are equivalent or equal. And you can certainly hear them saying, you get a new proof of this. But in practice, when we apply our proofs, we don't care what the proofs are. We use them as black boxes. We can now say, oh, the Poincare conjecture has a proof, and we can apply it, and we don't care which proof it is. The proofs of Fermat's last theorem have changed over the years. They've modified and simplified. But in some sense, there's only one. It's true. There's a tick by Fermat's last theorem. It's been proved. And in Lean, any two proofs of a proposition are equal by definition. So if A and B are types or sets, there's a different notion of equality, and this is some kind of notion of isomorphism or equivalence. So what does it mean for two types to be equivalent, or two sets to be equivalent, whatever your foundational system is? Two sets are equivalent if there are maps in both directions. If there's maps from A to B and maps from B to A, such that if you compose these maps, each of the compositions is the identity function. So an equivalence is like a bijection. And bijection is an equivalence relation. This is how I would explain it to a generic mathematician. Bijection between sets is easily checked to be an equivalence relation. And so if we think about this, equivalence is different to equality, right? I mean, classically at least, if I've got a set with n elements, then how many equivalences are there between this set and itself? N factorial. The number of bijections from a set of size n to itself is n factorial. Whereas there's only one proof of equality between a set and itself, because I don't know, at least in Lean, there can only be one proof of any theorem. So univalence says the following thing, which in this context looks slightly ridiculous. You see, in type theory, A equals A and A equivalent to A. These are both types. And in univalence, the univalence axiom is the axiom that these two types are equivalent. So equivalence is the same as equality. And in Lean's type theory, this immediately leads to a contradiction. So we can't have univalence in Lean's type theory, because the size of the set A equals B is 1, and the size of the set A equals A is 1, and the size of the set A is isomorphic to A is n factorial. So let A be bool, the set true, false. So that's what univalence is. Equivalence is the same as equality, and that's why it's not there in core Lean. So here's two empirical observations about univalence. Firstly, is one of the key proponents of this idea was a generic mathematician. Voivodsko got his Fields Medal for doing algebraic geometry. And secondly, consequences of the axiom are very, very natural. We'll see something showing up later where a mathematician kind of, in some sense, accidentally uses the univalence axiom, where Grothendieck uses univalence without even commenting. So univalence does show up when you're doing structural mathematics. And here's an example. Univalence is somehow surprisingly embedded in some funny way. Here's a question about complicated mathematical objects that I'm expecting essentially none of the audience to even know the definitions of, and yet I'm still hoping that there are people in the audience that can answer the question. So say A and B are Huber rings, whatever they are. They're mathematical structures, and let's say they're isomorphic. And let's say A satisfies a certain mathematical predicate, namely it's a strongly Noetherian Huber ring. And now the question is, the isomorphic Huber ring B, do you think it's also strongly Noetherian? And even if you don't know what any of those words mean, the very fact that a mathematician is prepared to ask that question means that strongly Noetherian is some kind of a valid mathematical concept. And so it means that it should be constant on isomorphism classes. So the answer to this question is yes, right? And even if you ask an undergraduate mathematician who has no idea what these mean, if you ask them to gamble on an answer, they're going to gamble on yes, because that's the way that mathematics works. So in Lean, we have to prove this theorem, and in Lean, it's a very tedious piece of work because the proof is a very long triviality. You just have to take apart the definitions of absolutely everything and verify that all the steps used to make these definitions. We never did anything that was not isomorphism invariant. So we have to write tactics that prove this kind of result. And that basic tactic arrived, it landed yesterday in Lean, but it's still a very, very primitive version. Mathematicians are going to have to learn how to use this tactic. And I still don't think, for example, that it would prove the example. But in a univalent system, we get the proof for free.
Excuse me, Kevin, we've got a question from David Yetter. Go, David.
You're rendering into sort of colloquial English of the univalence axiom.
Yeah.
Is that quite fair? I mean, shouldn't it be that, because that looks like, to me, like a rendering into English of the type A equals B is equal to the type A is equivalent to B.
Yeah, I'm absolutely. So here we are. Yeah, equality and isomorphism. Did I say it was the same? You see, I've chosen my words very carefully here.
Is the same?
Yeah, mathematicians use this concept of being the same in a very, very fluid way.
But I mean, the point is, it's the weaker than equality version that's asserted between the two. And
But mathematicians are very good at confusing the two concepts. And remember, I'm a mathematician. So, I mean, I know enough type theory to understand how to I can formalize this in one of these Coq libraries. I understand what it means, and I absolutely agree that I'm not using it.
Torsten, do you want to contribute?
Yes, please. Can I?
Yes, please go ahead.
Hello. Good to see you again. I just a little remark. I mean, in set theory, this thing. The theorem about these Huber rings, whatever they are, could be false, right? Because you could have a property which.
Absolutely.
Yes,
yeah, absolutely. But you know it's not false because if it was false, the concept of being strongly Noetherian just wouldn't exist in mathematics.
Yeah.
It would not be accepted by the generic mathematical community.
Right, but it's a bit of a vague thing. You know, it's a structural property.
Yeah.
And you could have, sometimes you have non-structural property. Also, in particular, you could get confused. Maybe for a sub kind, this is structural, but not for the other one, and then you transfer it. So it's very tricky to say that. I mean, this is basically something which is false, which people think it's true, but they could stumble upon this, right?
Completely. So what you're saying, what you're arguing is that of course we should be using HoTT because we should make pretty sure all of the concepts that we generic mathematicians introduce, we should make pretty darn sure that they are constant on isomorphism classes.
Yeah.
And if one tried to formalize them in a HoTT system, you would find that you wouldn't be able to formalize them if they weren't. HoTT is, so that's a great argument for the univalent axiom. It keeps you honest.
Okay, thank you.
Thanks, Torsten.
So in a univalent system, we're going to get this proof. If we can formalize the statement of this example, we can formalize the proof, right? Because if we know that A and B are isomorphic, then we know that we're equal. And so any predicate that any predicate on A, its value on A is going to be the same as its value on B.
Andy, Andy Pitts, do you want to say something?
Yeah, so just a remark. So what I'm deducing is that set theorists, and I mean that in the sense of people who do serious set theory, they're not actually generic mathematicians, are they?
No, I'm trying to rule those people out.
Okay.
In my definition.
Sorry for them.
No. I want to distinguish between the people who are in charge and the people who aren't, right?
The thing is, of course, those set theorists, they do some serious mathematics and they do get results about.
I really don't want to talk about serious. I mean, I absolutely agree that these people are. It's extremely difficult for me to find a phrase which is not upsetting people.
No, I'm not upset because I'm not one of them. But the remark I wanted to make is that it is possible that serious set theory produces results in generic mathematics, as it were.
Oh yes. In logic more generally, there have been spectacular examples of people, I mean, I remember Khrushchevsky just suddenly, these logicians appearing out of the woodwork and saying, oh, look, some of our theorems about O minimality have got non-trivial consequences in number theory. And you know, suddenly the number theorists have to take notice. I absolutely agree that logic can have non-trivial applications in what I'm calling generic mathematics. And this is exactly why I'm not calling it mathematics. You know, this is exactly, yeah, that's absolutely true, and I'm well aware of it.
Okay, yeah.
For some reason, I just want to distinguish between, you know, the uncomfortable fact is, when was the last time there was a Fields Medal awarded to set theory? Does that mean that set theorists aren't doing deep mathematics? No, I don't think it does. I think it means that, you know, set theorists are somehow, for some reason, you know, are not part of the, are not part of the cabal that's making the decisions about what's going on. I just don't really know why it's happening.
Thanks, Kevin. Okay, please carry on. It'd be good if we could wrap up in about 10 minutes, if that's possible.
Right. Oh, okay. Look at all these slides. Okay, so let's talk about localizing rings. So here's some mathematics. So this is what a ring is. It's a set equipped with addition, subtraction, and multiplication. And I'm not going to tell you what a scheme is, but Grothendieck came along in 1960 and postulated the notion of a scheme and revolutionized algebraic geometry. And one of the first constructions in the theory of schemes is that every commutative ring gives rise to a scheme. And some mathematics students and I formalized this construction in Lean, a system without univalence, and we ran into trouble at one point. And here's where we ran into trouble. So a ring has got addition, subtraction, and multiplication, like the integers, the rationals. But what about division? A ring doesn't have division. See, there, the integers are an example of a ring. And the true 2/3, the number that when you multiply it by 3, you get to 2 again, the true 2/3 is not in the ring Z, right? It's missing. But so if you really want to do 2 divided by 3 and get an object such that when you times it by 3, you get 2 again, you're going to have to enlarge Z. For example, you can use the rationals. You can move from the integers to the rationals. Or if you don't want to go so far, you can just throw in the thing you need. You need a reciprocal of 3. So you can instead look at the rational numbers A over B, such that the denominator was a power of 3. And one can easily check that this set is close under addition, subtraction, and multiplication. And so it's also a ring. It's a bigger ring where we can do our division. So, you know, and one way of making the rationals is by starting with the integers and then demanding that we can take the reciprocal of every single non-zero integer, or even just the positive integers bigger than 1, that would be enough. So what's the formal story here of localization? This is a relatively simple, mathematical story. We have a commutative ring, so addition, subtraction, and multiplication. And then we've got a subset of this ring consisting of the elements that we want to divide by. And our goal is to make a new ring where we've divided by the elements that we want to, where we can divide by the elements we want to divide by. So the first step is to take some kind of monoid closure of our set. So, sure, dividing by 1 is fine. And if we can divide by A and we can divide by B, then we want to, we can divide by A times B by just dividing by 1, then dividing by the other. So let's modify our set so it becomes a monoid. And now our naive guess for the localization, how are we going to make this new ring where we're allowed to divide by elements of S? We can just take pairs. We can take an element of R and an element of S. And we could just imagine the pair R, S corresponding to, the division R divided by S. So this naive guess isn't quite right because 1 divided by 2 is equal to 2 divided by 4 in the rationals, but the pair 1, 2 is not equal to the pair 2, 4. So of course we fix this by taking equivalence classes. We put an equivalence relation on the pairs R cross S. And the actual ring, R localized at S, is a quotient of this product by this equivalence relation. And there's this standard abusive notation. R1 over 3 is R1 over the set containing 3 and is R1 over, it's typical notational nightmare that one sees in generic mathematics. And so now here's an interesting observation. Let's say we've got a ring where we can invert 2 and we can invert 3. Then we clearly invert 6 because we can just multiply them together. And then conversely, if we can invert 6, then we can also invert 3 and we can invert 2 because twice a sixth is a third and 3 times a sixth is a half. So inverting 2 and inverting 3 is kind of the same thing as inverting 6. And when you formally chase that up, you find the following theorem, that if I take a ring R and then I invert 2 and I invert 3, I get the same ring as if I invert 6, right? These rings are equal. Any generic mathematician would be completely happy with that statement. And indeed, you even see this in Grothendieck's work on schemes, right from the very beginning, right from the beginning of EGA1. You can see David Roberts' is a Twitter timeline. He quoted it explicitly. Grothendieck is quite happy to assert that rings like this are equal, you see. And these rings are not actually equal. Because when you think about how they are literally made, we've got some set and some equivalence relations. And when you make R1 over 6, you've got some set which is all the powers of 6. And when you make R1 over 2, R1 over 3, the last thing you do is you've got some set of powers of 3, and then you have some product, and then you have some equivalence relations on these products. And these products are not the same. The equivalence relations are not the same. And these quotients, so formally speaking, are not literally the same thing. A mathematician would make an equivalence, would make a quotient by forming sets of equivalence classes. And these sets are not equal. However, they are isomorphic. In fact, there is more than isomorphic. These rings are canonically isomorphic, which is an informal but stronger notion of equivalence. You can make it formal in this particular context. You can say these rings satisfy the same universal property. So these rings are isomorphic. And this was something that had not occurred to me when I started formalizing. This is a subtlety that I had not been made aware of. So when we were formalizing the work of Grothendieck and Lean without univalence, we found that mathematicians would implicitly replace one of these rings by this isomorphic ring without any comment at all. And without univalence, we had to pay because we couldn't make that replacement. So we had to rewrite some proofs. In fact, we had to step back. We'd proved some theorems about a localization of a ring at a multiplicative set, and we had to rewrite those proofs so they didn't just literally apply to the construction we'd made, but they applied more generally to any ring which satisfied the universal property which our localization had. So we had to refactor our code. And this turned out to be a delicate argument in API extraction because the universal property is a rather unwieldy thing to deal with. It involves quantification over all rings. So there was a time when we wrote some pretty horrible code. And then Neil Strickland had some kind of insight which changed things. So here's Strickland's theorem. Strickland's theorem is just, I'm not going to go through Strickland's theorem. It's a basic theorem in ring theory. But Strickland's theorem, what it does is it characterizes which rings are localizations. It gives a very easy set of conditions which involve no quantification over all rings. It gives us 3 easy to verify conditions which can be used in practice. And these were the conditions that were being used in our proofs. So it wasn't so difficult to refactor our proofs. We had to change the statements, but changing the proofs was typically rather easy. So Strickland's proof was very easy. I mean, the hard part was isolating conditions 1, 2, and 3, which were the conditions we needed to build our API without too much trouble. But it involved a lot of API rebuilding when we realized that we couldn't make this substitution. And it turned out that, Strickland's API was the perfect API. We could build everything on top of it. So with univalence gives this prospect that actually things would have been much easier. We would have just been able to rewrite because our isomorphic rings would become equal and we could have replaced one of our rings with an equal ring. And maybe it all would have been much easier. But maybe somehow the carpet would have popped up somewhere else, right? That's the question. Would there have been other problems instead? And the answer to this question is that nobody actually knows. I've heard a lot of people theorizing about whether univalence will solve this problem in practice, but nobody actually knows because nobody tried yet. Nobody tried formalizing generic algebraic geometry in a theorem prover. So in summary then, univalence might be the secret sauce which makes generic mathematics more accessible and easier to do in theorem provers. But even though a lot of mathematics has been done, in these hot systems. And here I'm making the distinction. A lot of mathematics, a lot of deep mathematics, there's a huge amount of category theory. There's all this synthetic homotopy theory done in Voevodsky's theorem. There's a huge amount of mathematics being done in this system, but there's very little generic mathematics being done. You know, this traditional undergraduate mathematician stuff that the mathematics departments are teaching year in, year out. You know, great infinity topos theory, higher category theory, some serious stuff is being done in these univalent systems, but very little generic mathematics. And this is typically, I think, because of the people who are using the systems. And I think this has to change. Because mathematicians, we generic mathematicians, we need to know which system to use. And I just think maybe actually we should be using lots of systems. But in particular, I think it's time that we started using a homotopy type theory system. So there's a new chat room, which one of my generic mathematician friends set up, Johan Kommerlin. He set up a new chat room where a lot of homotopy type theory stuff gets discussed. And this is, I don't know, I could probably click on it. There you go, I could click on it and it would work. I won't do it just now. So in some sense, this wrap up is just an advert. It's an advert for this chat room. So Lean and Koch, it's doing it. Like Lean and Koch are doing generic mathematics. Hot systems are not. And I don't really understand why not. Having talked to many, many people, I really don't understand why it's not happening. I think it's just because the people aren't in place. Frank V. Dyke absolutely emphasizes that to do a serious amount of mathematics, we need to have a whole bunch of people working on one coherent whole. And Lean is doing this. Lean's maths library is a coherent whole with multiple people working on it via its GitHub interface. And it's time that we turn one of these hot theories into that. So will it be better with univalence? Nobody knows because we didn't try. And that's it.
Thank you very much, Kevin, for a fantastic talk. Now, what's going to happen is we're all going to applaud. I'm going to unmute everybody, and we can all applaud. Okay, is everybody ready? Let's see if this works. 3, 2, 1. Okay, that's enough of that. Right, so do we have any questions? We have a question from Phil Wadler. Let me just turn to your video. Phil, please go ahead.
Oh,
we can't hear you. We can't hear you, Philip. I'm afraid you're unmuted. Maybe I'll just turn to somebody else. Steve Vickers has a question. Go ahead, Steve.
Yeah, it's just a question about generic mathematicians. So the way I understand the word generic is it says we know nothing, no specific properties other than it's mathematics or it's mathematicians. And I think, you know,
mathematics with the axiom of choice. I think that's a good defining property of a generic mathematician.
Well, that's okay. This is where I'm worrying about the use of the word generic. Generic.
Yeah. I'm really sorry.
So I think if you start off with the subject matter and you say generic mathematics is topology and algebra and analysis, blah blah blah, then I can go along with that. But then when you say and you're using the axiom of choice and excluded middle and stuff, then that's kind of saying anyone who doesn't accept those is not a mathematician, really, even though they're doing that.
These people are clearly mathematicians, but the key point that needs to be emphasized is that in our undergraduate curriculum that I teach at my university, the axiom of choice is an axiom, and the law of the excluded middle is an axiom, and no attempt is ever made to ever even give the students the idea that there might be people that are not assuming these axioms. That's
but if
the uncomfortable truth of the matter.
If it changed, you know, if in who knows, tomorrow or a century's time, it was all different, people might still be doing the same topology and and algebra. It would look different because the methodology is different, but I think that would still be generic mathematics, even though it's different techniques.
What my point in isolating this, I can't, you know, in isolating this concept, I'm merely trying to say, I'm merely trying to draw some generic ring around the people that are in charge of funding, the people that are in charge of prizes.
Right.
I have no idea what the people that I want to become involved in formalizing because they're important, but they have no idea what the axioms of set theory are, and they have no idea what the law of the excluded middle is, beyond the fact that it's obviously true.
Okay, thanks, Steve. Maybe we can move to the next question. Paul Levy.
Hello.
Hi.
Thanks for the talk, Kevin. I just want to be clear about what you're saying, that your criticism of non-univalent systems, whether that should be set theory or non-univalent type theory, is not that they don't prove the things you want. All the things you want are theorems, but the proofs are either too long or too repetitive. And that's very different from the traditional criticisms of where you have arguments between constructivist and classical, which are about, is this thing provable or is this not provable? For you, all the things you want are already provable in ZSC, but they're just, it's a matter of having convenient proofs.
You see, I personally think that the solution is dependent types, no univalence, and better automation. But I would be very interested in finding a group of people that are so convinced that I'm wrong that they will start thinking about formalizing the definition of a scheme in a system that has univalence. Because I think it's very important. We only did it last year. An MSc student finished the job last year in Leans dependent type theory. I think it's about time somebody did it in a homotopy type theory. So we simply find out what the differences are.
Do you mind if we go to the next? Go to the next question, Paul?
No, that's it. I'm done. I'm done. Thank you.
Okay. Thanks very much, Paul. So the next question is from Andre Bauer.
Hi.
Hi. Hello. I just really have a comment, and so two comments, short comments. One is that, of course, excluded middle and the axiom of choice don't contradict univalence, so you can have those two, and in fact,
I know.
So that works. I mean, it's worth saying for everybody else out there.
But it finally dawned on me that this was the case. This is exactly why I thought I should give this talk.
Yes, and the other one is that the HoTT library, you already have examples where people at first used univalence, but then because univalence itself in Coq didn't compute, it didn't normalize as well, you didn't get judgmental equalities, they backpedaled on that, and they actually took the trouble of providing the explicit equivalences and going through all the manual work of having explicit equivalences in those places, because then you could convince the system that something worked nicely. Now, this is a deficiency of the HoTT library and the way that univalence doesn't compute in Coq. So I think it would be absolutely interesting to formalize this bit of algebraic geometry that you're suggesting, but also in a system where the univalence actually computes, because I think you would probably, I'm scared to think what kind of computation you would get there at the level of rings, and it would be a good reason to buy more supercomputers.
So cubical type theory, univalence.
Those are my comments.
But cubical type theory, univalence. Oh, please don't make him go, because I don't know anything about cubical type theory. This is a system where univalence computes.
Yes. Well, for instance, in cubical type theory, it computes, except we don't really have a full-fledged proof assistant that would do that. There are very nice prototypes. Agda is the furthest. Well, Agda, actually, the new Agda can do that. So it would be interesting to try that in Agda, yes.
So there you go. So there's absolutely Agda should be mentioned. It's not on the slides, but it's being mentioned in the audio. Let's try Agda and cubical type theory.
Maybe you can write up like a little short note that says what it is that you want these other mathematicians do, and so they can look at your PDF and say like, this, and this.
Sure.
Okay, I want to move to the next question now. Thanks very much. Thanks so much, Andre. The next question is from Rebecca Bellavin. Please go ahead. If you could start your video, that would be nice, but that's not essential.
Sorry, my internet connection is not great.
No problem. Please go ahead.
So, Kevin, you promised you were going to explain your plan for attacking this question.
Yeah, it's get people onto the chat room.
Oh, okay.
Click here. There's the plan. There, I have hearts all over my screen. There, yeah, this is my plan. We should start talking about it here. Yeah, are you in? Yeah, can you see? I'm now attempting to stream.
Yes, we can see that.
I absolutely think, and there you go. And see, there's like the number of people online is already filling. This has been an extremely successful chat room. I think there's people whose names you recognise here. Where's Reed Barton? Isn't that the canonical internet question? There he is, active now. So this is the solution. Just Ali. So Johan has already started formalizing basic results about rings, and Ali was just there helping him along doing it. And I think that, in a matter of weeks, if sufficiently many people to get involved, in a matter of weeks, using this chat room, we could absolutely build schemes in HoTT. I firmly believe that. I don't see any reason why not. That's the solution.
Okay, thank you, Rebecca, for your question. Okay, I'm going to take one more question from Neil Krishnaswamy. Do you want to go ahead, Neil? Sorry, I'm unable to unmute you. It's possible that you might have not given permissions for audio. I'll give you a few more seconds. Okay, that's not coming on. Okay, we have a question from Paul Taylor. Paul, would you like to go ahead?
Can you hear me?
I can.
Yes.
Can you hear me? Okay. The thing that turned me in or turned me off excluded middle was because I felt there was a lot of ugly things going on, ugly arguments involving excluded middle. I think the main argument for against excluded middle is that mathematics is prettier without it. If you have your proofs written by people possibly using excluded middle, there can be, in many cases, there are automated ways of reorganizing them. So one of the things that could happen if your project is successful would be to be getting automatically and a lot of more constructive arguments than there had been in the past. And then maybe once that has been done a lot, your generic mathematician would be a little bit more persuaded to argue in a more constructive way.
I absolutely agree that the law of the excluded middle is massively overused in mathematics, and actually mathematicians don't typically actually understand what a proof by contradiction is. 50% of the time they prove something by contradiction is not actually a proof by contradiction. But the problem is there are times when it's necessary. That a scheme is a topological space with a sheaf of rings, and to prove that that topological space is a topological space for the spectrum of a ring, it absolutely needs a non-constructive argument. And I think it's going to be very difficult to, if the only purpose of making a whole bunch of mathematics is constructive is just to make the proofs longer but more easily, but more computable, then there's going to be resistance to doing that, because mathematicians might like proofs which are more readable and they don't give a monkeys about whether they compute or not.
Okay, thanks, Kevin. I think we're going to finish the question and answer session there. I'm going to unmute again. Let's thank Kevin again very much for a fantastic talk. Okay.